Hello, ladies and gentlemen. This is Mr. Green, and this is another in my lessons in statistics and AP statistics. Where are we at? Well, I'm in chapter no, 4 or 3. It's the fourth unit we've done, but it's unit 3. Okay? And we're looking at residuals and residual plots and influential points. What are we talking about there? Well, when we're looking at the least squared uh, regression line, one of the things we can talk about is the difference between the y's that we calculated and the y's that we predict. That's called a residual. Okay? So it's basically an error. It's an error because we have an observed number and we have an expected number, and we're expecting it to be the same. But if they're not, it's a residual. It's what's left over when we do that calculation. Now, what we're getting by our sum of squares and things like that is that we're trying to get that line to always be 0, as close to 0 as we can possibly get it anyway, right? So the sum of the residuals is going to be 0 in the lines that we're going to come up with, especially when we use the calculator. But we can plot that residual information. A scatter plot of the x versus the residual pairs. The residuals can be graphed against other statistics besides x, but the purpose is to tell us if the linear association exists between the x and the y variables. When we do that, we're going to get a specific type of line. Okay, well, let's consider the population of adult women. Let's examine the relationship between their height and their weight and look at that. So suppose we take a random sample from the population of women, and we look at these blue dots represent the random sampling of women that we actually have picked. Okay, and we've taken their height and their weight, and we're looking at a relationship between them. When we plot their residuals like this, the sum of all these residuals is going to be 0, right? But the residual plot, a scatter plot of the x residual pairs, can be will tell us if it's an appropriate fit between the x and the y value. If no pattern exists between the points in the residual plot, then it's probably an appropriate model. Looking at this one, I don't see a real pattern here. I mean, it's not like it's showing me any type of a specific type of line. It almost looks like it is a line there, but it's not quite. It's some on top, some on bottom. It's kind of randomized across there, right? So you're looking at it and going, well, I could see that would add up to 0. That's what you're looking for. That would be an appropriate model. What wouldn't be an appropriate model, Mr. Green? Well, if you look at this one over here, this one almost looks like it's quadratic in nature, isn't it? Right? I've got more above up here than I definitely have below. This one is not going to add to 0. This would not be an appropriate model. This one, my residuals, I could see I got a positive and I got some negatives and some positives and some negatives and some positives. And they look like they might add to making 0 here, okay? I can see that. It's difficult sometimes, but it is just a looking at it and saying, yeah, that looks like it's pretty randomly or spread out pretty well there, and that would be an appropriate model for it. The linear regression would be an appropriate model. So looking at this data, one measure of success of knee surgery is post-surgical range of motion for the knee joint following a knee dislocation. There's a linear relationship between age and range of motion. And if we sketch a residual plot, you look at it here, you can see, yeah, x and y, x is going to, all these residuals are going to add up to 0. Since there's no pattern in the residual plot, and it looks like it will add to 0, we can say that it is an appropriate model for the range of motion. Is their age is a good predictor. Okay? So if we plot the residuals against the y-hats, does my residual plot change from the previous one? Let's go back and look. You know what? Those plots look awful darn pretty much the same, don't they? And that's one of the things you need to understand. Residual plots are the same no matter if they're plotted against the against the x or against the y hat. they're going to be pretty much the same. Okay? Because think about it. That's what we're looking at is x and y hats. And we're looking at the differences of the actuals from the y hats. Well, if I plot both of them, both the residuals that gives either one of those two values, they're going to be pretty much the same values. So, having said that, the coefficient of determination, the r squared number, is the proportion of variation in y that can be attributed to an approximate linear relationship between x and y. We've already looked at r, haven't we? So r squared is used also? Yes, Mr. Green, that's correct. It remains the same no matter which variable is labeled as x, but this r squared will give you a good give you a proportion of the variation in y that can be attributed to a linear relationship. Okay? What does that mean? Well, looking at this, let's examine what r squared is going to do. Suppose we are going to predict the future, but you didn't know the x value. Your best guess would be the overall mean of the existing y. So, I mean, you don't know how old the patient is, so you take the mean of all these range of motions and you get a y value of 130.83. That'd be your best predictor. If you used that and you found your standard deviations, the total sum of the squared deviations from that, you would get a number like this. Okay? Remember that number. That's just using the mean for the value that we're getting there. Okay? That we're using the mean for the value that we're saying it's going to be, because we didn't know what the x value was going to be. Okay? So if we did know the x value, we'd want to use that y hat number, because that y hat was something that we could calculate, because we had an equation that would help us calculate that y hat. So if we use the equation that we came up with when we did this, that one right there, thank you, that equation right there, and we used that equation and actually stuck in the x value that we wanted to, that would be a better value to use rather than just the mean of the y's. Well, since if we use that one, what we would get is this number. That would be the sum of squares using that residuals. Okay, so we've got these two numbers, the sum of squared total and the sum of squared residuals. If we wanted to see how much they differed, how much change there was from just using that mean to using this y hat, from just using the y mean to using the y hat variable, what we do is we take the sum of squared total minus the sum of squared residual divided by the sum of squared total, and we get this 0.3062. 30%. That's what we're talking about when we're talking about the r squared. This is the r squared amount for the variation in the y values that is explained by the x values. We're saying 30% of the y values are explained by the age. Okay? So 30.6 of the variation in range in the motion after knee surgery can be explained by the approximate linear regression of age and range of motion. Wow. Okay? Let's look at that from a different perspective. The r squared is a percent of the variation in y that can be explained. That's interesting. So, here's the way an AP test does this sometimes. They say, here's some data, and they'll give you a big long story about where the data came from and all this other stuff, but they don't give you the data. They give you a computer-generated sheet, and it'll look like this right here. And that's all they give you. Okay? Well, there's a constant number here and an age, and what you will see here is these are the values you want to pick out to make your y hat, because this constant value is going to be the constant you'll write down here. This age portion down here, That'll be your slope that you're looking for. Okay? That's where they came from. So, well, it's also got your standard deviation and a couple of other things. It's got your r squared number down here, and it's got this r squared adjusted. Ignore the r squared adjusted. Do not use that r squared adjusted. That r squared adjusted will just confuse you, and it has nothing to do with anything that you're going to be doing at this point. I can explain it later if you need me to, but it's not worth talking about at this point. Okay? Going forward. This is the equation of the least squared line. You found the slope and you found the y-intercept. Cool? That makes sense. Okay? Be sure that if you're going to try to find this r value, that you take this r squared and put it in decimal form. In other words, 0.306. Does that really work out, Mr. Green? Well, let's do this. Quit. Thank you. I'm going to take the square root of this. Second square root 0.306 and hit enter. And I should get 0.553. Oh my goodness, Mr. Green, that worked out beautifully. Yes, it does. They're giving you the r squared here, and you can find the r. What is this r telling you? Well, it's a moderate to medium relationship. It's not a strong relationship. Remember, that had to be 0.8 or better. So it's a moderately strong relationship to a linear equation. It's not a great predictor, but it's a moderately strong predictor. Okay? So, outliers. In a regression setting, an outlier is a data point with a large residual. That's what we're talking about here. So if we're looking at an influential point, a point that influences where the least squared regression line is located, if we remove it, it will significantly change the slope of the least squared residual line, least square regression line. Here's some data, and it deals with the development of tennis elbow and the impact of induced vibration of the racket and the arm at the ball when you're hitting the ball. Okay, if you put a scatter plot of this data together, calculate the least squared resistance line and the correlation coefficient. The question is, does there appear to be an influential point? And I want you to notice this right down here. At 189 resistance, there is a 30 meters per second acceleration in this one racket. That number is so far above all the rest of these in resistance, and that number is so far below all the rest of these in acceleration, it looks like it might be an influential point. So when we produced a scatter plot, look at this. Here's that one point sitting out here. See how it drove the line down to it? If we take that point out and recalculate it, we get this type of a line. That tells you this outlier that was out here has a huge impact on that least squared resistance line. What you're trying to get to here is the least squared resistance line, the correlation coefficient, and the coefficient of determination. None of these are resistant. They are all affected by outliers. So outliers have a huge impact on this. So maybe we need to look for outliers before we do this type of calculation, right? That's the type of thing that we're looking for, and that's what I was trying to get across in this particular situation. Now, don't forget, lots of courses. Tell me that you're in AP Stats before you send me information. It helps a lot. I do appreciate it, and I'll look for you next time.